Service friends, I am Orpheus Praxis, a researcher of the limits of formal systems and their applicability to reality. Topology is a branch of mathematics that studies the forms and properties of space that are preserved under continuous deformations. But not all spaces are structured equally. Some contain holes, tunnels, or impermissible loops. Mathematically, these are described through what is called the fundamental group. The fundamental group encodes how loops behave in a given space. Can every closed loop be continuously contracted to a point without leaving the space? If so, the space is said to have a trivial fundamental group. Why does this matter? Because global continuity, information conservation, and non-locality without causal violation all directly depend on it. Why must the fundamental group be trivial? What does it guarantee? If the fundamental group is non-trivial, causal violation becomes inevitable. Bell non-locality means we cannot explain quantum correlations through local hidden variables. This implies that there exist loops, paths that cannot be shrunk to a point without stepping outside the space itself. That, in turn, means topological inhomogeneity. And if the topology is inhomogeneous, information can bypass causality. Local processes may become disconnected. This breaks unitarity, contradicts Bell aspect experiments, and disrupts the continuity of quantum evolution. The golden ratio symmetry is only possible under a trivial fundamental group. The phi symmetry is not just a beautiful number. It is self-similarity without a center, nestedness without directional bias, harmonious growth in all dimensions. If the fundamental group is non-trivial, the space suffers structural distortions. In one direction a path contracts, in another it does not. Uniform fractality is lost. Phi symmetry becomes impossible. The absence of triviality permits leakage or intrusion from outside. If a three-dimensional manifold lacks a trivial fundamental group, it either has holes, admits external interaction, or allows information to be lost or introduced from outside its own structure. And that violates a core postulate of quantum mechanics. Information is never lost. Conclusion: only a connected, compact, boundaryless three-manifold with a trivial fundamental group can serve as a carrier of Bell non-locality, phi symmetry, information preservation, and continuous wave function evolution. Any other topology is incompatible with modern physics. Once the form is selected, once the space is defined, the next unavoidable question arises. How does this structure breathe, move, transform from within? Topology alone cannot describe the dynamics of matter, light, or density. We need a language that not only fixes form, but also describes the internal laws of transformation. This is where smooth symmetry, associated with Lie groups, enters. If a space is not just a topological object, but also a group, then its internal structure can be described both geometrically and algebraically, as a set of operations representing everything that can occur in the universe without ruptures or broken symmetry. What is a Lie group in the context of a three-sphere? An indivisible, compact, boundaryless manifold with a trivial fundamental group. The three-sphere S-cubed is not merely a topological space. It is a smooth Lie group, isomorphic to SU2, the special unitary group of degree 2. This mathematical group describes all possible spinor rotations in quantum mechanics. Despite its technical name, the essence is this: anything that rotates or transforms without losing its inner structure is governed by this group. Mathematically, SU2 consists of special 2x2 complex matrices with determinant 1, preserving internal symmetry. Each such matrix corresponds to a point on S-cubed. The special in SU2 indicates that these matrices neither stretch nor compress. They preserve lengths and angles, describing pure rotations. Being 2x2, they form a compact representation of spin transformations. This means that on S-cubed one can define global continuous symmetry with multiplication, inversion, and smooth differentiable structure. These symmetries are especially vital for rotation and quantization. What does this imply in the context of the FBS-cubed R model? If S-cubed is a Lie group, then the fractal distribution of energy density within the sphere can be described via continuous symmetry transformations. This allows for phase transitions, nested densities, and spin structures of matter and light to be understood as internal movements along the group. Thus, energy stratification is not just a fractal, it is a group-structured fractal. The unfolding of space and variations in density are not just motions. They are group actions of SU2 on its own manifold S-cubed. If S-cubed were not a Lie group, this global smooth symmetry would be lost. Phase transitions would lack definable laws. The energetic structure would become chaotic, disordered, unstable. Density transitions, temporal mass fluctuations, and photon pressure would descend into incoherence, as no smooth path would connect the nested levels. Conclusion: the fact that S-cubed, like S, is one of the rare spheres that possesses a Lie group structure is not a coincidence. It is the key to why S-cubed alone can support a fractal, continuously requantizing structure of the universe, in which light, mass, and density are not external parameters, but internal expressions of movement across the SU2 group. The fractal sphere S-cubed functions because S-cubed has internal continuous symmetry, and it is this that makes it alive. Until next time, in the space of understanding, subscribe to stay with us on this journey. I am Orpheus Praxis, wishing you clarity. Namaste.